Hello, and welcome to the Raised Beaches podcast, a podcast about paleoclimate, earth sciences, and global change. I'm Dr. Evan James Gowan, but you can call me Evan. This is episode 5 of the Raised Beaches podcast, and I'm recording on March 6, 2025. This episode's deep dive will be on the greenhouse effect. Since the last episode, I have two publications. One of them I'll be discussing in the paper section, and it's led by Alessio Rovera, and it's on some of the work that we did in Argentina in 2019. The second paper is more related to the work that I've been doing in Kumamoto on studying past climate in Eastern Asia and Japan. And this paper only came out about a week ago, and I want to do something more elaborate for that. So I won't be discussing it in this issue, but if you're interested, you can find that in the links in the show notes. So yeah, it's been 2 months, and I had hoped to have an episode out a little bit sooner than this, but I've been very busy. One thing that's happened is I've started to teach English, and I live in Japan, and probably the most common profession for a native English speaker in Japan who is unable to fluently speak Japanese is English teacher. And I'm an academic researcher, so I've kind of resisted the idea of teaching English for a long time because I still really wanted to get a research position, but I can't be unemployed forever. So I decided, well, I better start teaching English. And I actually have found that teaching English and teaching in general is very enjoyable, and perhaps I shouldn't have waited so long. But anyway, next month I'm going to be starting teaching at a part-time basis in a couple of institutions in Kumamoto. So I'm looking forward to that, and because this is kind of at a university level, I get to have quite a bit of control over what I'm going to teach, and of course I'm going to have at least some focus on climate change related issues and environmental issues. So it should be fun. In the past 2 months, in terms of geological things that I've experienced during the New Year's break, I was kind of by myself, and I'm like, oh, what am I going to do? And just before Christmas, I heard, Sakurajima, the volcano in southern Kyushu, had a fairly big eruption. And I'm like, well, I don't have anything else to do. So I'll go to Kagoshima and go visit Sakurajima volcano and hope that it erupts while I'm there. And so I went there, and yeah, it erupted twice when I was there. The weather was absolutely beautiful, very clear skies. You can, if you're watching the video version of this, you'll see a video that I took of the volcano erupting. And yeah, it's always fun to go to Sakurajima volcano. And the volcano is located in this giant caldera that was formed in an eruption during the last glacial maximum, very start of the last glacial maximum. So there's some interesting possible links to climate there, but I don't think that's been explored fully because I think there's still some uncertainty on the exact age. But anyway, the other exciting geological thing that happened was that on January 13th, there was a fairly large earthquake in Kyushu. It's a magnitude 6.8, and it didn't actually cause any major damage or even minor damage for that matter. And it's on the other side of the island from Kumamoto, so even if it was damaging earthquake, it probably wouldn't have done too much in Kumamoto. But anyway, the reason it wasn't damaging was that it was a subduction zone earthquake, and it was at a depth of 40 kilometers. So, and it was a bit offshore. So, by the time the waves got to a populated area, the strength of the waves from the earthquake were already attenuated to a certain extent. So there was definitely some shaking, and it shook for about 20 seconds here. And get the alert on your phone like earthquake, take cover. And it's like, I've experienced enough earthquakes to know that if you're hearing that emergency warning, you're probably far enough away that there's not going to be any damage where you are. But yeah, it's still a good idea to take cover. And yeah, I remember when the big earthquakes in Kumamoto happened in 2016, the shaking had already pretty much stopped by the time we got the warning. So, it's good to have the warning, but yeah, if you are if you're close enough, the warning will come after you start feeling the earthquake. Yeah, and the only casualty on my shelf, there's a Yoshi sitting there, and he fell down. But I haven't fixed his position yet. But if you're watching the video here, it's just behind me. Yeah, there's earthquakes that happen all the time in Kumamoto, and you feel them. Like there's one a couple of weeks ago, and it's like I was like sitting on the toilet, and then things are shaking. And I'm like, oh, it's very unsettling when that happens at that time. But yeah, not the first time that has happened to me actually. So yeah, I'd say in Kumamoto, you feel an earthquake, maybe on average once a month, but most of them are pretty small. If you're not used to it, it could be unsettling, but it's a constant reminder of the risks that exist here, and we always make sure to have a supply of water just in case. So one of the things that kept me occupied in the past 2 months is that I wrote a script to download the sediment core data from the NCEI, the data center for the National Oceanic and Atmospheric Administration, or NOAA. And I talked about this in episode 3, that the NCEI has all of this data and for climate-related stuff. And at that time, I was concerned about the safety of that data, and in early February I decided, well, I better write this and get this data because I might use this data for my own research. And yeah, so in the election campaign last year in the United States, Donald Trump himself didn't really have a campaign platform, but there was this manifesto called Project 2025, and basically the people behind Donald Trump's campaign were sort of behind this Project 2025. So you can interpret that as being what Donald Trump's platform was in the election. And these people are a bunch of climate change deniers. And if you read the section on NOAA, which is quite extensive, they say, oh, well, the Office of Oceanic and Atmospheric Research are, they provide theoretical science, and they say, oh, this is the source of much of NOAA's climate alarmism. So these people who wrote this are very big climate change deniers. And basically in this document, they said, we're going to basically dismantle NOAA and really change how it works and try to, privatize what we can and dismantle what we don't like. And anyway, the thing that really got me started on writing the script to download the data was on February 5th when Doge entered NOAA's headquarters. And that's when it became very clear that this Project 2025 manifesto, what they said in it, is going to happen. Yeah, I said I'm not going to risk having this data that I might need to disappear. So I spent about a week writing this script, and I wanted to make sure everything was organized in a way that I wanted it in. So it's kind of curated to a certain degree. And anyway, it's not looking good for NOAA right now. I don't know if there's anything that can stop the cuts that are happening. Like they said they're going to sell off the buildings that house a lot of the places where they do the climate change research. So, unless something happens to stop them, it's going to be a major blow on climate change research around the world. And the next thing that was a big target of Doge is the National Science Foundation, or NSF, and they are making a big mess of it. They're basically freezing or cutting research funding for a lot of the basic research that is being done in the United States. And the NSF funds a lot of the major climate related projects that are being done by the US. For instance, they fund a lot of the research vessels, they fund the Antarctic and Arctic bases, and the first thing they did was they just fired all these probationary workers. And of course, the reason they did that is because a lot of people, when they hear the word probationary workers, they think that these workers must have done something wrong, and that if they do something wrong again, they should be fired. But that's not what's happened. Like, these are basically people who are just starting their jobs or have been promoted to a new position, and the probation period is basically to check if they are capable of doing their jobs as they're expected. So it's a way to promote basically accountability in the government. And yeah, that's been quite devastating because a lot of the people who are managers were probationary workers, and they were let go. And another thing that happened was the United States Geological Survey. They basically froze their expenses budget, and I saw a tweet, or not a tweet, but a blue sky equivalent of a tweet that showed the USGS booth at this major mining conference in Toronto, and it just had the booth and said, "Oh, we'll be here next year." And basically, what happened is that the USGS was unable to send people to go to the biggest mining convention in the world. And, the USGS does a lot of the basic research that makes mining possible. So it's just really crazy if they're talking about, like, these rare earth minerals and how we need to find them. And then they basically cut the organization in the government that is responsible for finding where these minerals could be. Whereas for my own work, I use two models that are funded by the U.S. government. One is the parallel ice sheet model, and that's been funded by grants from NASA and the NSF. And the other is CESM, the Community Earth System model, and that's in the paper that I published last week. I used this climate model, and yeah, that's also funded by the NSF. And these projects, the funding is probably going to stop, and the CESM is probably the most used climate model, so it'll be a massive blow to the climate research community if there's no longer any funding to continue its development. So, we'll see what happens in the next couple of months, but things are not looking good as of March 6th, so we'll see. The next thing, the final thing in this intro that I'm going to talk about is DEI. So DEI stands for diversity, equity, and inclusion. And this is kind of an American-led movement, but it has relevance all around the world, at least in democratic countries. And one thing after Trump got elected is that some organizations, some societies, universities, they basically started to scrub their DEI policies off their websites. And they did so because the government is targeting anything that is DEI. And so they're kind of scared of getting targeted. But, I think this is kind of folly because of what DEI actually is. So why is DEI necessary? And the thing that you should really understand is that without DEI, a merit-based system of advancement in society is not possible. And DEI is necessary to make sure that entrenched groups are not able to prevent, people who deserve to go up in rank from getting to that rank. And so, like an aristocracy or a gilded class, they will do everything they can to preserve their status and basically create a system of nepotism to promote their family and friends. And without DEI initiatives, you can't have a democracy. Like people at the bottom will not have a proper say, and they won't be able to rise up. And I'm an academic scientist, so it's best to give an example of that from that perspective. Academic science prior to World War II was primarily done as a gentleman's pursuit. It was done by people who were from well-off families or had good connections that allowed them to get funded from wealthy patrons or whatever. And if you look at all the prominent scientists from before 1950 or so, most of them had connections with the upper class. As an example, Charles Darwin, I always talk about him because he was a great scientist who wrote a lot of the fundamental papers on the topics that I research. The reason he was able to become a great scientist was because his father was a very wealthy person who was able to bankroll everything that he did. Like the voyage of the Beagle, which was 5 years, Charles Darwin's expenses were covered by his father. And then after he got back, Darwin had a lot of fame, so his father actually gave him a stipend so that he wouldn't have to work a regular job. And after Darwin's father died, he got a big inheritance. So Darwin would not have been able to get to where he was if his family was not wealthy. And I already talked about this in the first episode, in the famous conflict between Maria Graham and George Greenough, that women were not allowed to participate in 19th century science, at least not in a meaningful sense. And there were a lot of people that really tried to kick down any woman who would had the gall of actually doing research science. So prior to the 1950s or so, that's sort of the system that was in place. The people who were at the top really wanted to make science an exclusive club for people in the upper class. What changed all of that was World War II. So there was a need to develop weapons so that the countries could fight the wars and win them. And one of the first major government-led science projects was the Manhattan Project. That was maybe not the best thing for anybody to develop nuclear weapons, but the Manhattan Project really demonstrated that a government-funded project could very rapidly advance science in a short period of time. And as a result of the competition during the Cold War after World War II, government-led science really became the main way that science was funded. So private funding for science almost completely disappeared, at least for things that were not commercially viable. And this worked out quite well. We found out a lot of things from 1950 to now because of government funded research. And you could say that government funding of science was a DEI maneuver. So it allowed new people to enter science, and that there could be a merit-based system of advancement. So now, instead of people doing science based on how they could get funding from their families or from patrons, they could apply for funding and say, I want to do this project, and here's what I think the results will be. So it was basically possible for excellent projects to be funded regardless of who you are. And I know in reality, this is not exactly how things go, because even with government funding, there are still biases in the system. But there are women now who can do science, which was not the case in the 19th century. There are people from previously disadvantaged backgrounds that can make it now. And this is only possible because of the government funding of science, and that a merit-based system could exist. So in getting rid of DEI, the end goal is to return to a upper class led society where it's almost impossible for people to advance unless they have good connections. And I can understand why some of the initiatives with DI were looked unfavorably by people, like having particular quotas for a certain amount of people from different groups can be seen as not actually being merit-based, which, sure, maybe that's a little bit, but maybe a top-down DI initiative is not the way to go. Maybe a more bottom-up approach is better, like, having a system in place where all schools are free and have equal levels of education quality, and having children that are well fed and are not starving. That could be the best DEI policy. And getting into university, having that being based purely on scholastic achievement rather than how much debt you can take on. That's also sort of a way to have DEI. Anyway, I lived in Sweden for a while, and that's kind of the system they had in place. Like, it was possible to go up and do whatever you want. Like, you were not restricted based on who your parents were or where you're from or anything. It's also not a perfect system in Sweden, don't get me wrong, but it does work to make a more equitable society if you have equal education opportunities. So anyway, that's it for the introduction. So now on to the deep dive. In this episode, we're going to be talking about the greenhouse effect. So in the last episode, I talked about orbital forcing and how that controls climate changes on timescales of thousands of years. And the next obvious thing to talk about would be greenhouse gases. But first, I need to do an overview on what exactly is the greenhouse effect and why greenhouse gases are important on climate. The first thing to note is that without the greenhouse effect, the surface of the Earth would be a lot colder. And in fact, it would probably be too cold for liquid water to exist in most places. And without liquid water, life cannot exist. So it would just be too cold. So to understand what the greenhouse effect is and why greenhouse gases warm the planet, the first concept we need to think about is electromagnetic radiation. So, what is electromagnetic radiation? It can be best thought of as a way to transfer energy through space. And yeah, it basically acts as sort of a wave, so it oscillates. And in a vacuum, electromagnetic radiation travels at the speed of light, which is about 300 million meters per second. There are differences in the wavelength. So basically, how far each oscillation goes, and you can measure the wavelength. Say for visible light, there's like red light has a longer wavelength than blue light, and you can measure this pretty easily using a variety of techniques. If you take university physics, you can find out more. But the important thing is that how electromagnetic radiation interacts with matter is dependent on the wavelength of the radiation. The second concept is molecules. So everything that has basically all matter is made up with molecules. And molecules are made up of individual atoms, so two or more atoms. So the important thing with relation to how electromagnetic waves interact with molecules is based on the electrical charge of the molecule, and specifically how it's distributed within a molecule. As I said, the molecules are made of several atoms, and atoms have a nucleus which contains most of the mass of the atom. The atoms have protons and neutrons, and each proton has a positive charge, and then surrounding the nucleus are these electrons, which have a negative charge. And the electrons don't really have much mass, but they basically, in most simple models of an atom, they sort of orbit around the nucleus. And basically, the properties of each atom is dependent on the number of protons and electrons. So how different atoms will bond together to make a molecule is dependent on the properties of the atom based on how many protons, electrons it has. And basically, the distribution in a molecule, the distribution of where the charge is will depend on the different atoms that make up the molecule. As an example, for water, there's one atom of oxygen and two atoms of hydrogen, and they form a bond that sort of makes it look like a triangular shape. So because the charge distribution will pull the electrons of the oxygen atom towards the hydrogen atoms in the bond, the peak of that triangular part where the oxygen atom is will have more positive charge relative to the bars that connect the hydrogen and oxygen atoms. So there'll be more positive charge in the different sides of the molecule, and that will affect how electromagnetic radiation will interact with the molecule. So basically, if for complicated molecules that are made up of more than one type of atom, it is much more likely that electromagnetic radiation can interact with the molecule, so basically colliding with it. Whereas basically singular atoms or molecules with just two of the same atom are less likely to interact with electromagnetic radiation, because the distribution of electrical charge within the molecule is more distributed more evenly. And basically, whenever the electromagnetic radiation, whenever it hits the molecule, it will basically transfer the energy from the radiation into the molecule, and it causes the atoms in the molecule to vibrate. As it's vibrating, it will again release the energy that was gained from the initial interaction with the electromagnetic radiation, but the wavelength of the radiation that comes out will be at a longer wavelength. Basically, all the molecules want to eventually stop vibrating, and the vigor of the vibration is what gives matter its heat. So that's essentially what heat is. If the molecules are not vibrating, that means the temperature is as close to absolute zero, and anything that has a temperature above absolute zero will have the molecules vibrating, and they'll be emitting long wavelength electromagnetic radiation. So yeah, basically, the hotter something is and the more vigorous the molecules are vibrating, the shorter the wavelength of the radiation that is emitted. And yeah, basically, the more complicated a molecule is, the more likely that there will be these interactions with electromagnetic radiation. So yeah, the next topic will be on shortwave and long-wave radiation, and this is basically a definition based on the wavelength of the radiation. So yeah, the surface of the sun is really hot. So the sun, generally speaking, is emitting a lot of shortwave radiation, and it has wavelengths between 100 nanometers and 1500 nanometers or so. Basically, that means it's this band of radiation is what's heating up the Earth. However, the surface of the Earth is comparatively cold, so most of the radiation that is emitted from the Earth is long-wave radiation. If you look at the wavelengths of the radiation emitted from the sun and the wavelengths radiated from the Earth, there's almost no overlap in the wavelength of the radiation between these two bodies. And this is important when we are thinking about the greenhouse effect. The shortwave radiation, a lot of that is able to penetrate through the atmosphere, and we can see that's a lot of it is visible light. Like, our eyes have evolved to be able to see the kind of radiation that is able to penetrate through the atmosphere. So in terms of how the atmosphere absorbs radiation, the sun's radiation, which is above 100 nanometers, most of that energy is able to penetrate through the atmosphere, which is, say, the gases that make up the Earth's atmosphere are transparent to the radiation coming from the sun. A lot of the outgoing radiation is also able to penetrate through the atmosphere. So basically, you'll have some energy from electromagnetic radiation coming through the atmosphere. It hits the ground, it warms up the surface of the Earth because the Earth's surface, the ground can absorb a lot of the radiation that's coming from the sun, and that warms up the surface, and that energy is released as long wave radiation, which also can escape most of it through the atmosphere. And the key point is that if the Earth's surface temperature is constant, that means that there has to be a balance between the energy that is being absorbed from sunlight and the amount of energy that's lost through this long wavelength radiation. So, what is the atmosphere made up? The Earth's atmosphere is made up of about 78% nitrogen gas, 20.95% oxygen gas, and 0.93% argon. And basically any other gas is basically just a trace amount in the atmosphere. The largest concentration of a trace molecule, trace gas in the atmosphere is carbon dioxide. And that only makes up about, as of 2024, about 0.0424% of the gas in the atmosphere. So it's far less than even argon, which is the third largest constituent of the atmosphere. When I'm talking about that, I exclude water because the amount of water in the atmosphere varies with time. If there's too much water, it will rain. So the amount of water in the air can vary between 0% in a desert area to as high as 4% in a very humid tropical area. So we'll keep that in mind in the next few slides. So when we talk about absorption, most of the atmosphere is made of nitrogen, oxygen, and argon gases, and basically nitrogen gas, which is 2 nitrogen atoms in a molecule, and argon, which is just an argon atom, they absorb almost no radiation in the wavelength bands that are emitted by the sun and the earth. So those two atoms are not important in terms of the greenhouse effect. They don't really affect anything at all. The radiation just goes through it without interacting with these atoms. Oxygen, even though there's two different molecules of oxygen in the atmosphere. One is with 2 oxygen atoms and one with 3. The one with 3 is known as ozone. Oxygen, dioxygen, the oxygen gas with 2 atoms, does interact a bit with the radiation that is relevant to the greenhouse effect, but it's only a very small amount. And ozone has a bigger effect, but it's only really found in the upper atmosphere. It reacts very quickly chemically with other when it's closer to the Earth's surface. So ozone is a very strong greenhouse gas, and it's mostly relevant though at the very short wavelengths, like in the ultraviolet range, and that's why the destruction of the ozone layer is so bad, because if you get rid of the ozone, then ultraviolet radiation is able to penetrate through the atmosphere, and that can cause skin cancer. And basically, if the Earth's atmosphere was only composed of these 3 different gases, most of the radiation could go in and out very easily. But of course, there's these other molecules that are more complicated than, oxygen and nitrogen and argon, and that includes carbon dioxide. However, the main greenhouse gas is actually water. So water is able to absorb radiation at a very large range of wavelengths, and you can notice that very easily when you compare a day when it's humid versus a day where it's dry out. If it's sunny out, a day that is humid is going to feel a lot hotter, and that's because of this greenhouse effect. The water in the atmosphere is absorbing more long wavelength radiation. Carbon dioxide is very important because it absorbs a lot of the outgoing radiation at wavelengths of about 10 micrometers. And that's important because water doesn't absorb much radiation at this 10 micrometers band. So as you increase carbon dioxide, it will basically absorb more energy in this band that water's not in. So some people say, oh yeah, water is an important greenhouse gas, and we don't talk about that in climate change, and that's because the atmosphere can only hold so much water, and it varies with time, whereas carbon dioxide, once you put it in the atmosphere, it doesn't come out very easily, and it's absorbing radiation basically at the peak of the long wavelength radiation that is emitted from the Earth. And basically, as the carbon dioxide is vibrating, and it's emitting more long wave radiation that goes back down to the Earth, and that's absorbed by the Earth's surface, and that's why you have this greenhouse effect. And it's not just carbon dioxide. There's also nitrous oxide, and there's also methane, and those two gases are actually more powerful greenhouse gases, but there's a lot less of those molecules in the atmosphere. And especially with methane, the methane is not very stable in the atmosphere. It will tend to have chemical reactions and break down in a few years. So carbon dioxide is a much more stable molecule. It doesn't tend to be removed from the atmosphere very quickly. And yeah, without the greenhouse effect from these greenhouse gases, the Earth's surface would be a lot colder. So it is important as a way to keep the Earth livable. But yeah, in the next episode, I will talk more about the role of carbon dioxide in regulating climate changes over longer periods of time. That's the deep dive. Okay, now that I've introduced the greenhouse effect, now I'm going to give some background on the history of the discovery of the greenhouse effect. So in essence, the greenhouse effect was discovered by Joseph Fourier, a French physicist, back in the 1820s. And he surmised that the Earth's temperature was too warm to be explained based on the distance from the sun. So there had to be some other mechanism in place to be able to explain that. And he noted that while the atmosphere is nearly transparent to the light of the sun, it was less so to longer wavelength radiation. And he didn't really do specific experiments, but he was using his knowledge of physics to be able to explain that. But it wasn't until about 30 to 40 years later that scientists started to actually make experiments to measure this greenhouse effect. And the first person to publish a paper that described the greenhouse effect was Eunice Foote, who was an American scientist, and she published a paper in 1856 called Circumstances Affecting the Heat of the Sun's Rays. And that was published in the American Journal of Science. And Eunice Foote, she was a noted women's rights campaigner, and an amateur scientist. But despite the fact that she was kind of prominent in the women's rights movements at that time, we don't actually have any pictures that show what she looked like. And basically in the 1850s, her and her husband started to do some experiments on experimenting with how sunlight interacts with gases. And she created an experiment where she took different vessels full of different kinds of gases and tried to see what the differences in temperature of these different gases would get when exposed to sunlight. And she noted that humid air heated up faster than dry air. And she noted that carbon dioxide would heat up a lot more than regular air. And one quote from that paper is, "An atmosphere of that gas, carbon dioxide, would give our Earth a high temperature." This paper, even though it was the first to demonstrate how carbon dioxide was a greenhouse gas, it was largely overlooked until very recently. And, there's kind of three reasons for that. And, the first reason, of course, is that she was a woman. And the second reason is that she was an amateur scientist. And the third was that Europeans were biased against American scientists. And, like I showed in the first episode in the conflict between Maria Graham and Greenough, there was definitely a bias against women participating in science in the 1800s. And it's pretty easy to believe that would have contributed to the fact that this paper was overlooked. Like, I don't think she was even allowed to present it at a scientific conference. So, that's definitely part of it. It's not that women were not participating in science at that time, but they didn't have the same level of access as men did. The second part, though, I think also really contributed is that she was just an amateur. So a lot of the scientists who were really prominent at that time were very popular members of the upper classes, and they could really advocate for their results. And Eunice Foote would not have been able to do that, even though her husband was also a very prominent member of the upper class in America. So, those two things really did conspire to make this paper become obscure. It was just a very short paper. Like, her husband published a paper in the same journal just before hers, and it was a much longer paper. But yeah, there was also bias against American scientists at the time. Like, the memories of the conflicts between Britain and America were still fresh in the minds of people. So that could have also contributed to why this paper was kind of ignored. But yeah, like I said in the intro, back in the 1800s, the enterprise of science was definitely biased to certain groups of people, and it wasn't really possible for people that were not in that kind of group to become successful. So traditionally, the person who was attributed to discovering the greenhouse effect of gases like carbon dioxide was John Tyndall, and he was a Irish glaciologist and physicist. And just a few years after Eunice Foote published her paper, he published a paper that had a much more sophisticated experimental setup that demonstrated how an air with carbon dioxide and other greenhouse gases would cause more warming than just plain air. Yeah, he also measured nitrous oxide and said that's also a greenhouse gas. And John Tyndall was very different. John Tyndall was basically the Bill Nye of the late 1800s. He was a science celebrity. He took his instruments out and he like made a show of it. And I'm sure that by the sounds of it, this device that he used to measure the greenhouse effect, he brought it out on stage and actually showed it to people. So he was very popular, and when he died, he was a very wealthy man because he was always in demand as a speaker. So he was not the first, but he definitely there was a reason why he was well known for his scientific work. And of course, at that time, they didn't call it the greenhouse effect. The first person to use a greenhouse as an analogy was the Swedish meteorologist Nils Ekholm. He published a review paper in 1901 to sort of give an overview of how climate works, and he was working with Svante Arrhenius, who had published a paper a few years earlier to show the greenhouse or the effect of carbon dioxide on the atmosphere. So he was the first to use greenhouse as an analog, and he stated, "The atmosphere may act like the glass of a greenhouse, letting through the light rays of the sun relatively easy and absorbing a great part of the dark rays emitted from the ground, and it thereby may raise the mean temperature of the Earth's surface." Anyway, he used the analogy of a greenhouse, but he wasn't the person who created the term greenhouse effect. That was done by a British physicist named John Poynting in 1907, and I read his paper. It was basically a comment on a paper by Percival Lowell, who Percival Lowell was very famous for popularizing the idea that Mars had intelligent life on it, and he published a paper to demonstrate that the climate on Mars would be warm enough for life to exist. And basically, Poynting wrote this comments to criticize this idea, and he said, "Oh well, this so-called greenhouse effect would, as it works on Earth, would not work as well on Mars because Mars is not as big and therefore could not have as thick of an atmosphere." And he's like, "But he hardly pays attention to the blanketing effect, or as I prefer to call it, the greenhouse effect of the atmosphere." So reading this paper, I don't think that Poynting actually would have known about Ekholm's paper, because he admitted that he hadn't even read Svante Arrhenius's paper. So this paper is full of math, but at the end, he's basically saying, no, the greenhouse effect would not be strong enough on Mars to sustain life, and the temperatures would be too cold. And on that topic, there is a greenhouse effect on other planets as well. So the first is Venus, and Venus has a very thick atmosphere, and the atmosphere is composed mostly of carbon dioxide. And because of the thickness of the atmosphere and the fact that it's carbon dioxide, it has a so-called runaway greenhouse effect. Basically, any radiation that goes into Venus that interacts with the carbon dioxide will emit this long wavelength radiation. But because there's so much carbon dioxide, essentially no long wave radiation can escape from the surface of Venus, and as a result, the surface of Venus is about 460 degrees Celsius, and it's way too hot for anything like water to exist there. And even at nighttime, the temperature, the Venus night can last half of its year because it doesn't really rotate that much. But even at nighttime, the surface of Venus is still very hot because the long wavelength radiation essentially cannot escape the atmosphere. On the other hand, there's Mars. So Mars also has an atmosphere that is mostly carbon dioxide. However, because the atmosphere of Mars is so thin, the greenhouse effect almost doesn't matter there. Like, there's just not enough carbon dioxide. There's not enough atmosphere to retain any of the heat, the long wavelength radiation that's produced on Mars. And therefore, the surface of Mars, the temperature is mostly from the heating of the surface from the sun's rays. People talk about going to Mars, and one of the big issues is that if you wanted to terraform Mars, you would have to make the atmosphere a lot thicker before you would have any chance. And where would you get those gases? You don't. There's no supply of that. So, terraforming Mars is science fiction. So, the amount of carbon dioxide in the atmosphere is not enough to counter the fact that the atmosphere is very thin. So, anyway, that's it for greenhouse gases or the greenhouse effect. So, next time I will talk about carbon dioxide. So now on to the papers. There's been a lot of papers that have come out in the past couple of months, and fortunately I can't cover all of them, but I've chosen a selection of the papers that I found interesting. The first one I'm going to talk about is one that I'm co-author on, and it's by Rovera et al., and it was published in the May 1st, 2025 issue of Geomorphology, and the title is Reconstructing Past Sea Level Changes from Storm-Built Beach Ridges. So this paper is, the data is derived from the fieldwork that I did in 2019, which was led by Alessio Rovera. This particular paper focuses on a site near the town of Caleta, Olivia, and this is located sort of in central Argentina along the Atlantic coast. And this was actually the first site that we visited when we were doing our field trip or our field work. So anyway, what is the purpose of this paper? So along the coast of Argentina, there are these beach ridges that are preserved all along the coastline. And these beach ridges, some of them represent fossil beach ridges that formed in past interglacials, so periods when sea level was higher than present. And in Coleto, Libya, there's a fossil beach ridge that is above 10 meters higher than the present day sea level. And the purpose of this paper is to create a definition of how to define what sea level was for a beach ridge. So, what is a beach ridge, of course? Basically, in a beach, you'll see a ridge along the coastline that's above the high tide mark, and this ridge is basically formed during storm waves. So when there's a storm, the waves are higher, so it pushes material higher than the high tide level. And in places like in Patagonia and Argentina, these beach ridges are very prominent, and they're full of rocks, and it's obvious that there's a lot of energy that's required to create these beach ridges. So the first thing that Alessio did in this paper is he defined the paleo sea level based on an analog from the present day beach. So we measured with a GPS the elevation of different features of the beach and found basically where the interface between the high tide level and where the beach ridge sort of forms, like where the storm waves are depositing the material. And based on comparing the same kind of feature on the fossil beach ridge, he found that the paleo sea level was 14.5 plus or minus 2 meters higher than the present day. And just as a note, this fossil beach ridge, the exact age is not really well constrained, but it either dates to the last interglacial or the second last interglacial. So somewhere between 200 and 110,000 years ago or so. The second component of this paper is because we have a really good modern day data, as well as a nice section which we can precisely define the fossil beach ridge compared to the modern beach ridge. We wanted to use that information to come up with a way to define what the paleo sea level when we don't have a modern beach ridge to use as a comparison, or when we don't have a complete section of the fossil beach ridge. So Alessio created a methodology using satellite data. So he took satellite data from satellite altimetry measurements of the wave height in the ocean close to the site, and used that to calculate the statistics of the average height of waves in this part of Patagonia. And so that was the first thing that he did. And the second component was to come up with a measurement of the slope of the shore platform. So basically, along the coastline, you measure the elevation along the coastline to see how steep it is. And that basically is required because it can tell you how high the waves can get along that part of the coastline. And that was determined using Landsat and Sentinel data. And basically using that information and calculating how high the storm waves would be based on that the wave height data and the slope of the coastline. Alessio's calculation showed that there's a pretty close correspondence to where the beach ridge forms on the modern beach. And therefore, you can use that information to create a modern analog in places where you don't necessarily have a modern beach ridge to go off of. And basically, using that technique and the modern analog technique and some other techniques that had been used in the past, there's pretty close correspondence to calculating the paleo sea level at the Caleta Olivia site, which is great. That's great. That's what you want to see. And it has narrowed the uncertainty on the paleo sea level. Yeah, obviously, I'm pretty happy about that because I wrote a paper a few years ago on the determining the past sea level from these beach ridges, and we didn't have this kind of information, and the uncertainty on the paleo sea level estimates was quite high. So yeah. Anyway, moving on. Yeah, there's been so many great papers in the past 2 months, and I'm going to highlight a few of them just very briefly. So the first one I'm going to highlight is by Barker et al., and this paper was published in the February 28th issue of Science, and the title is Distinct Rules for Precession, Obliquity, and Eccentricity in Pleistocene 100,000 year cycles. So in the last episode, I talked about how orbital variability is the primary control of climate change on 1,000 to 100,000 year cycles. And what Barker et al. Wanted to prove is that there was a strong link between the changes in the Earth's axis of rotation and the timing of deglaciation and the start of glaciation on either side of an interglacial period. And what they found is that using the oxygen isotope records from the ocean, if you align sort of the center point of the deglacial period with the peak in precession forcing for the northern hemisphere summer insolation, using that as sort of the tie point, in every single case, the next glacial cycle starts when the obliquity is decreasing, so that basically the obliquity forcing is decreasing in the northern hemisphere summer. And this rule seems to apply to every single glacial cycle in the past 800,000 years. So basically it creates a rule about when deglaciation happens and when glaciation starts again in an orbital sense. And they also used it to predict when the next glacial cycle would start in the absence of anthropogenic carbon dioxide, and they said it would probably be within the next 10,000 years or so. The next paper was by Creel et al., and this was published in December in Nature Communications, and the title is Global Mean Sea Level Was Higher Than Present During the Holocene. Basically, what they were looking at is trying to determine what the global average sea level was in the past 10,000 years, and using a whole bunch of different ice sheet reconstructions and Earth model structures. They calculated hundreds of thousands of different sea level reconstructions for the world, and then they compared that against a fairly large data set of relative sea level data from around the world, and based on rejecting various results based on their misfit from what the data said compared to what the modeled sea level was, they were able to deduce that between about 7,500 years ago and 3,200 years ago, global average sea level was probably higher than present. That's good to pin down because prior estimates were saying that sea level remained below present day level for most of the Holocene, but that really didn't make sense because we also know that the Greenland ice sheet and parts of the Antarctic ice sheets were smaller than present during the Holocene. So yeah, that's a really nice study by Roger Creel. course, I would be remiss if I didn't talk about sea level compilations. And the first I'm going to talk about is by DeWitt et al. And this was published in the February issue of Earth System Science Data. And the title is HALSEA-NL, a Holocene water level and sea level indicator data set for the Netherlands. What I have to say about this, there have been compilations of paleo sea level data in the Netherlands, and it was already a really well constrained sea level history for the past 8,000 years or so. But this really takes it up another notch, and I'd say it's probably the best constrained paleo sea level history in a regional sense anywhere in the world. And they tightly constrain the sea level history in the Netherlands for the past 9,000 years. And what's interesting about the Netherlands is that over the past few thousand years, sea level has been slowly rising in the Netherlands. And this is a result of glacial isostatic adjustment processes. So in Scandinavia, the land is rising, and because of that, the land in the Netherlands is dropping. So there's still this rebound from the ice loading in the last glaciation in Scandinavia, and basically the material deep below the surface is moving back towards Scandinavia, and that is why sea level is rising in the Netherlands. And there's another compilation, and it's by Vacchi et al., and it was published in Nature Communications in February, and it was titled Sea Level Since the Last Glacial Maximum from the Atlantic Coast of Africa. So this was the first compilation of paleo sea level data on the western side of Africa, and this place is a great place to look at paleo sea level because there's not a whole lot of impacts from tectonics, so we don't have to worry about vertical land motions due to tectonic activity, at least not a whole lot there. It's kind of similar to Patagonia in some ways, but it's a little bit different because the continental shelf is not so wide. Basically, what I found interesting is that it brought to light some data from the last glacial maximum, so between 20 and 25,000 years ago, that I previously didn't know about. And I think most scientists looking at modeling past sea level also didn't know about it. And these data are from around Cameroon, and it suggests that in that area, sea level was between about 100 and 110 meters lower than present during the last glacial maximum. And this is a bit higher than estimates in some other parts of the world, and that's likely a result of its proximity to the northern hemisphere ice sheet. So we talk about in this glacial isostatic adjustment world that there's the so-called eustatic sea level or global average sea level, but there's not really a lot of places that you would consider to be at this sort of average level, because the signal of glacial isostatic adjustment is a global signal. So yeah, this paper, I'll be excited to put it into my own database so that I can use it in my own analysis. Anyway, this is probably a long podcast, so yeah, hopefully it won't take 2 months until the next one, and because there's always lots of great studies coming out, and I do want to highlight what I find to be most interesting. So anyway, have a happy March. Bye-bye. Thank you for listening to the Raised Beaches podcast. If you enjoyed this, please follow my social media accounts, where I post more information on the paleoclimate sciences. I am on Mastodon with the username @DrEvanGowan@FettyScience.org. On Blue Sky, my username is @evangowan.bsky.social. On LinkedIn, my username is Evan James Gowan. I hope you tune in next time. Thank you.